Thank you very much for the honor of the invitation. We're very happy to see that there's so many people that are interested in our overclocking exploits. This is John, as Dan already mentioned. My name's Peter, and this is the very first 9 GHz CPU. So today we're going to share a little bit about the story about how we achieved the first 9 GHz CPU. We'll first cover a little bit of the history of the CPU frequency overclocking world record to provide you some context on what was the journey over the past 3 decades. Then we'll tell you a little bit more about the challenges that are involved with trying to achieve a world record using liquid helium cooling. And then to end with, we'll also talk a little bit about the challenges involved and the opportunities that are there to go beyond 9 GHz, right? But to kick things off, let's first start by reliving the moment where we hit the 9 GHz for the first time.
That's right. This side? Okay. Let's try again. Let's try again. 1 point higher. Yeah. Try it? Yeah. Okay. One more. Oh boy. Let's see. Yes! 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 9 GHz. Ooh! 9 GHz. First 9 GHz.
All right. So that was quite a pleasant moment for us, as you could have seen. I apologize for anyone who is wearing headphones. So yeah, as I said, we'll walk through a brief history of the CPU frequency overclocking world record, talk a little bit about what Raptor Lake brought to the overclocking game, then explain what it takes to chase world records using liquid helium, and then end with what we can do to go beyond 9 GHz. So let's first have a couple of minutes and talk about the history of the CPU frequency overclocking world record. And the world record for CPU frequency is a record that has been contested for many, many years. Actually, the first competitive overclockers to chase the frequency record started all the way at the end of the previous millennium. So we're talking about 1995 and 1996, where some Japanese overclockers were already using liquid nitrogen to try and achieve the highest possible frequencies. Obviously not at 8 GHz, but at maybe 500, 600 megahertz, and so on. And the biggest improvement in the CPU frequency world record happened in the first part of the 2000s, so 2000 to 2005, where also on the industry side, there was a big push to achieve higher and higher frequencies. So as you can see here, in only a time span of about 8 years, we went from the first 1 GHz all the way to the first 8 GHz. And then as the frequency race transitioned into the multi-core era, there was a little bit of a stagnation when it comes to the maximum possible frequency. And that's quite well illustrated by the fact that it took us another 5 years to improve just 10%. So we went from 8 GHz to almost 8.8 GHz. That's not for a lack of trying among the overclockers. Every new CPU architecture, overclockers from around the world trying to find the best CPUs and use cooling techniques like liquid nitrogen and liquid helium to achieve the maximum possible frequency. But those architectures that came around in the multi-core era never really got to 8 GHz again. Alder Lake came the closest, but it was only 7.8 GHz. But then came Raptor Lake. And Raptor Lake kind of changed up the game when it comes to this frequency overclocking world record. So as you know, as I just told you, the frequency record for 12th gen for Alder Lake was 7.8 GHz. Within or inside the multi-core era, very respectable, a very high frequency, but not quite the 8 GHz. And then during the Intel Innovation 2022 event, Raptor Lake was introduced And there were two key announcements during that presentation that gave extra motivation to overclockers to try and push the frequency record higher using Raptor Lake. First big announcement was that you guys would release the first 6 gigahertz out-of-the-box CPU. Second important announcement was that Raptor Lake would use an improved Intel 7 process that would add 600 megahertz of turbo on top of what was already achieved with Alder Lake, right? So if we get 600 megahertz more on top of the 7.8 gigahertz that we already achieved with Alder Lake, then we would get to 8.4 gigahertz, maybe if we're lucky, 8.5 gigahertz. But then overclockers took Raptor Lake for a spin, pushed it as much as possible, and right on the launch of Raptor Lake, the 10-year-old record fell. So for the first time in a decade, we achieved 8.8 gigahertz. In fact, it was the very first 8.8 gigahertz, as the previous record was 8,794. Now, of course, breaking the overclocking world record is extremely exciting, and everyone's very happy about it, obviously. But there was something to be even more ecstatic about. The 8.8 gigahertz was achieved with liquid nitrogen, not with liquid helium. And so achieving 8.8 gigahertz on liquid nitrogen provided us with the hope that by going to even more extreme cooling methods, we could possibly see the first 9 gigahertz, right? Using liquid helium is a non-trivial activity. It's not as, I would say, simple as using liquid nitrogen, where you can essentially pour it into your cooling pot and have it sit there and do other things at the same time. Liquid helium evaporates very quickly, so and it's also a lot colder, so there's a lot of extra challenges that come with it. The obvious reason why you would want to use liquid helium is that it provides additional thermal headroom. So between liquid nitrogen and liquid helium, there's about a 70-degree Kelvin improvement in temperature. And as every overclocker knows, lower temperature means higher frequency, right? But what does it take to try and achieve a world record using liquid helium? What is involved in setting up that entire record attempt? And it's not just picking one CPU and then applying liquid helium on top of it, and then you have the record. There's actually quite a bit of steps involved in setting up the record attempt. There's 3 key ingredients that come into play when you try to achieve a world record using liquid helium. The first, and probably the most important ingredient, is that you need the perfect CPU. You don't need just any CPU. You need the one with the highest overclocking headroom. You need one that can scale properly with voltage. You need one that can scale properly with temperature. You need one that can handle those low temperatures as well. So the 9 gigahertz CPU that we used, we could, all right, here I said it's a 1 out of 10,000. It might as well be 1 out of a million chip that has all of these different characteristics in one sample. The second ingredient is that you need to manage those extreme temperatures. We're talking about temperatures all the way down to minus 250 degrees Celsius. So you'll deal with temperature-related issues such as cold boot bug. For those who don't know, cold bug is when the temperature is so low that the processor stops operating. Cold boot bug is when the temperature is so low that the CPU no longer wants to boot up. Obviously, you also need to be worried about condensation so that there's no short circuit on your motherboard. And in addition to that, you need to have all of the different components of your system be able to handle such low temperatures. So it's not just a matter of your CPU being able to run at minus 250 degrees Celsius. Your motherboard also needs to be able to do that. Your temperature is very closely located to your CPU. That will also cool down. So you need to manage those extreme temperatures. And then lastly, you need to do very proper time management. With liquid nitrogen, it's pretty easy to get a couple 100 liters in the lab and use it for several hours. Totally different game with liquid helium. For a typical record attempt, we would get about 100 liters of liquid helium. The cost of that is about $5,000 in Taiwan. It might be a little bit more expensive here in the US. And that gives us about 1 hour of runtime. So if we don't get the record in that 1 hour of runtime, either you spend more money or your shot is gone, right? In addition to handling the time pressure at the day itself, there's also quite a bit of preparation that comes into play for such a Helium attempt. So for our record attempts, usually the preparation starts a couple of weeks before, where we first find, let's say, 20 chips with decent overclocking characteristics. You try to find those that have the best potential, but you haven't really characterized them in detail. And then a couple of days before the record attempt, you start looking at each of the processor samples that you have in greater detail. You'll try and characterize each of the cores. You'll try and characterize which are the ones that scale with voltage. You'll try to characterize those that have problems with temperatures, and so on. Then on the record day itself, before doing the liquid helium, you want to replicate the identical process of overclocking your best processor and see if you can achieve still the same frequency. So you want to make sure that everything, every step of the overclocking process can be replicated over and over and over again. And then if everything works out, then you apply the liquid helium. And even with the liquid helium process, you need to make sure that your steps are well thought out. So normally you'll say, we'll have a target temperature, let's say minus 220 degrees. We have a target frequency. You apply the frequency. And then if it works out, slightly go up. If it doesn't work out, maybe you have to try a lower temperature. But so every step of the overclocking process is very well thought out, and everything needs to be, you need to be able to replicate each of these steps. If you have all of this worked out, if you have the perfect CPU and you've worked out all of your steps and you have the liquid helium, then you can improve your overclocking record. So with this 8.8 gigahertz CPU, we have a Q&A afterwards, so maybe we can do that. So if you have the perfect CPU that can run 8.8 gigahertz with liquid nitrogen, you can, the CPU scales incredibly well with temperature. You can run it at minus 250 degrees Celsius, about 20 degrees Kelvin above absolute zero. You add 200 megahertz, and for the first time, you can see 9 gigahertz. Over the lifetime of Raptor Lake, obviously there were some improvements in the manufacturing process. We were able to test more and more CPUs. So to this date, we've found 3 CPUs that can surpass 9 gigahertz, one of which can surpass 9.1 gigahertz. If you want to learn more or have a little bit more of a background information about all of these different sessions that we did, the Intel Technology YouTube team has actually, they flew out to Taiwan to record our sessions. And there's actually quite a lot of background information in those videos as well that will hopefully, if you watch them, give you a good impression of the vibe that goes on during such an event. So that's for the story about how we achieved the record, provided you with a little bit of context. Now the obvious question is, you guys hit 9 gigahertz, what's next, right? So here's where John will provide you with some information.
Yeah, so after 9 gigahertz, obviously, comes 10 gigahertz, right? Not quite so simple. We've looked a lot into, how do we get these frequency records? How do we measure frequency? We had an issue early on with Alder Lake, where there was an FLL problem where the requested ratio didn't quite apply. The FLL wasn't able to run that high of a frequency. So we could apply basically any ratio, but the CPU would still be stable, operating at an actual about 7 gigahertz frequency. Certain performance counters would also read this normally, so we started looking a lot into, how do you measure frequency? What is, the actual clock frequency of the chip? And this, led us down into a bit of a rabbit hole. Fortunately for Alder Lake, this issue was fixed by the Intel overclocking team for launch. So this was something we discovered, working with the ASUS overclocking team before launch, having the record ready for the Raptor Lake, for the Alder Lake launch. So it turns out measuring frequency is not that simple nowadays. The processors are so complicated. There are so many technologies going into power saving, opportunistic boosting and things like that, that it's not, your CPU is not running at one single frequency. You have very fast transitions and different criteria for when you run what frequency, and this happens like much quicker than a human can interpret. So the traditional way to measure processor frequency is to measure the base clock, or to read the base clock and then multiply it by what's the currently applied ratio that you can read back from the CPU. This would usually be done at 2-second intervals, primarily to reduce the load on the CPU when you're measuring. Also because, as a human, you're only able to see so many changes. The problem with this is that during those 2 seconds where you're not measuring the CPU frequency or not seeing the CPU frequency, a lot of things happen inside the CPU. So it doesn't really give an accurate picture of your CPU frequency anymore. So you're missing a lot of data that in terms of what frequency the CPU is operating at each point. You also have a bit of an observer effect. So like when you're reading these registers, you're loading the CPU and may cause the frequency to change. So one thing we found that can mitigate some of these problems is to use something called effective clock measurement, which is something we worked together with CPUC and HWInfo developers to integrate into their software to give us and others a little bit better of a picture of what's going on with your processor. So this method for frequency measurement it's using on-chip counters that would increment with the core clocks. So each executed clock is counted by the counter. So you can measure the number of clocks over a time period and determine an equivalent fixed clock frequency, while it's actually changing a lot during that time. And we call this effective clock measurement. So how this would work, as an example, is like your CPU is running at 1 gigahertz for half a second, then it's running at 2 gigahertz for another half a second. And the equivalent fixed clock frequency would be that it's running at 1.5 gigahertz for the full duration. Another approach we had to try to see what, how can we verify that what we're reading from the CPU is actually real, that it's, this is the frequency the CPU is running at, and we can verify it independently. So one of the methods we came up with was to try to benchmark it, right? So like, of course you can measure performance, but it's very taxing on the CPU if you run, we're trying to do very high frequency validation, so we want as little load as possible on the processor. And we want to be able to measure as close as possible to our target frequency. So one method we came up with is to measure the instruction execution rate. So we found using NOP instructions, which is as the least amount of load you can put on the CPU while still executing an instruction. Then we measure, like we run, for example, 100,000 iterations of a NOP, measures how long it takes, multiplied by a factor depending on the architecture for the IPC, and we get a value of what the CPU frequency was during this execution. This obviously has some issues, like we need to adapt it for every architecture to get a proper value, like have a different multiplier. You can't measure it while the CPU is executing something else, so like you have to have a fully idle core to get an accurate value. But in terms of validating the frequencies, like we can make sure we have a high confidence in that the processor is actually running the frequency that we're measuring in software. like in CPU software or HW info software. We found this to be a very useful tool. We have a proof of concept software of this. If anyone's interested in that, we can share some source code with you. If you have suggestions on how we could improve it, maybe we're very open to that. Additionally, we realized that the more complicated a CPU becomes, the more challenging it becomes to enable overclocking. So you go more and more towards an SoC, like a black box, everything's integrated. That takes a lot of work from, well, you guys and your partners to enable overclocking. We have all sorts of issues that stem from this, like you have an integrated voltage regulator. How is that going to deal with these extreme temperatures that we want to run? You have quality of life things like improving the thermal interface. So like having solar TIM, for example, on CPUs really helps us out to get these records. Makes our life a lot easier. So we really appreciate the job you guys are doing to help us out in this endeavor. And yeah, I think with that we can finish up. If you guys have some questions, now's the time.